Hello and welcome back. These will be the notes for 11-2, Simplifying Radical Expressions. There is a PDF available if you'd like to follow along and print it out. And one of the things I do recommend you memorizing perfect square numbers. So 4, 9, 16, 25, things like that, perfect squares. That will really help with simplifying radicals. There is an alternative method we can use if necessary. Anyway, simplifying radical expressions. A radical expression is one that uses a radical symbol, and this is the symbol here. And of course, the line that we normally see above it just tells us what we're taking the square root or radical of. A radical expression is in simplest form if the following conditions are true. There are no perfect squares under the radical or in the radicand. And when we say the radicand, we're talking about the part that is underneath the radical sign. There are no fractions in the radicand also, so it can't be any fractions inside there. And there could be no radicals in the denominator of a fraction. So if you have a fraction that has a radical in the denominator, it's not been simplified. One of our properties we're going to be using is called the product property of radicals. It says that the square root of a product equals the product of the square root of the factors. What does that mean? Well, if we have an example here of square root of a times b, then that is equal to the same thing as square root of a and the square root of b separate, and then timesing them together. But in both cases, a and b have to be bigger than 0, because keep in mind that we cannot have negative numbers under the radical. If we did, there's no solution. You cannot take the square root of a negative. First example here, we've got the square root of 4 times x, or 4x. Well, I can break that apart as the square root of 4 times the square root of x. This is still going to be equivalent to the original problem. However, the square root of 4 is a perfect square, and the square root of 4 is 2. And I can write it as 2 times the square root of x, because x is not a perfect square. But when I have a times between them, I'll just write them side by side like this, as if the radical is one big variable itself. So 2 square root of x means 2 times square root of x. Example 1a, simplifying radical expressions. What we need to do is look at that square root of 32 and think of what factors of 32 are perfect squares. So I can call this the same thing as 16 times 2, square root of 16 times 2, which in turn means I can call it the square root of 16 times the square root of 2. And the reason I'm going to call it that is because this right here is a perfect square. Well, the square root of 16 is 4, and then I still have a times the square root of 2 left over. So this right here is the simplified form of the square root of 32. So if you know your multiplication tables really well, and then you can figure out what the perfect squares are, then you can figure out things like the 16 here. Same thing down here on b, the square root of 9x cubed. What I'm going to do is break that into factors that are perfect squares and non-perfect squares. So the first thing is square root of 9 and the square root of x cubed. Well, the square root of x cubed can be broken down even further. Square root of 9, I can call it the square root of x squared times the square root of x to the first. So it's one big multiplication. The first two here are perfect squares. So the square root of 9 is going to give me 3, and the square root of x squared is going to give me x, and I still have a square root of x underneath the radical, because x to the first by itself is not a perfect square. So anything that's not a perfect square stays under the radical sign. Example 2a, simplifying radical expressions. Here's when we time. So I have a square root of 6 times square root of 6. Now these are irrational numbers, and since I'm multiplying, I can actually multiply irrationals with irrationals. Well, that would mean I can rewrite that again as square root of 6 times 6, which is equal to square root of 36, which in itself is a perfect square, which is just 6. Same thing down here. Remember, there is a 1 right here, so I'm going to do the 1 times the 4, which is 4, and then I can rewrite underneath it square root of 3x times x, which is going to be 4 square root of 3x squared. Well, since the x squared is a perfect square, I can write that as 4 square root of x squared times the square root of 3. This is a perfect square, so the square root of x squared is just x. And 4 times the x that's coming out of that perfect square, and then times by the square root of 3 left over. And this becomes the simplified answer of the original problem. Okay, same thing up here on letter C. We have a 1 out in front, so 3 times 1 is just going to give us 3. And then underneath the radical sign, I'm going to multiply my x with this x here, and that will give me a 7x squared y squared. Well, the x squared and the y squared are both perfect squares, so I'm going to call them the square root of x squared times the square root of y squared times the square root of 7. And both of these here are perfect squares, which will come out as x and y. So 3 times x times y. And then I still have a square root of 7 because that's not a perfect square and it stays underneath the radical, and that becomes my simplified answer. The quotient property of radicals. The square root of a quotient, which is nothing more than a division, equals the quotient of the square roots of the numerator and the denominator. So if I have a fraction underneath the radical sign like this, and remember, to be in simplified form, we're not allowed to have fractions under the radicals. We break it out into a fraction with a radical in the top and a radical in the bottom. Again, we cannot have a's that are negative, and we cannot have b's that are negative or 0, because b is in the denominator, and we can't have a denominator of 0 either. So here's an example. Square root of 16 25ths is the same thing as the square root of 16 over the square root of 25. And the square root of 16, of course, is 4, and the square root of 25 is 5. And this ends up being the simplified version of that. Example 3, I'm going to rewrite this as the square root of 13 over the square root of 100. And 13 is not a perfect square, so all I can do is just leave it as the square root of 13. The denominator is a perfect square. Square root of 100 is 10, and this ends up being my simplified radical. B, I can't have a fraction under there, so I'm going to write it as the quotient of the numerator and this quotient of the denominator. Like this. And the denominator happens to be a perfect square. X to the second power is a perfect square, so the square root of 7 over x. Square root of x squared is just x. And this ends up being my simplified answer. Example 4, rationalizing the denominator. If you remember that one of our rules or one of our conditions to be simplified, the denominator cannot have any radicals in it. Well, in this case, we see that there's a radical down there. The biggest problem is the 7 itself is not a perfect square, so we cannot just take it out. However, we can use a technique that we've seen before with fractions to simplify that. If I can take a number and times it by itself, well, the answer that comes out of it is a perfect square. So all I'm going to do to fix this is to multiply the top and the bottom by the square root of 7 over the square root of 7. Now remember, that is equal to 1, which means I'm not really changing the value of the number because I'm multiplying it by something that is equal to 1. So if I multiply across, I get a 5 times the square root of 7. Now do not take this 5 and try to multiply it with the 7 inside. This part of the problem is a rational number. This part of the problem is irrational. And all I can do is express them with a multiplication. I can't actually multiply the 5 and the 7 together. And some people will try to do that. On the bottom, when I do the square root of 7 times the square root of 7, what I get is a square root of 7 squared. Or if you want to call it 49, that's fine. You can call it 49. Let's go ahead and do that. Get the square root of 49. And now the denominator is a perfect square, which means I can simplify it to just 7. So the simplified answer would be 5 square root of 7 over 7. And the same thing down here on example B. Square root of 3b is not a perfect square. So I'm going to multiply it by the square root of 3b over the square root of 3b. Multiply across the top. Now, this number and this number are both irrational, so now I can actually even take the 2 and times it with the 3, and the 2 times 3 is going to give me 6b, and I still have that underneath the radical. So I have the square root of 6b in the top. In the bottom, I have the square root of 9b squared. As it turns out, both of these numbers down here are perfect squares. So if I take the square root of 9 and the square root of b squared, I ended up with 3b. So the final answer is the square root of 6b over 3b. Example 5, add and subtract radicals. Now here's where it becomes really difficult. We've said before that the numbers outside are called rational numbers, and the numbers under the radical signs are called irrationals, and we cannot combine them together. But we need to treat anything that's under the radical sign as if it were the same thing as a variable. So pretend that these are variables. Anything that has a radical that's the same underneath the radical sign is a like term with other radicals at the same number underneath the sign. So if I'm going to simplify this, I see that I have a square root of 10 up in the front and up in the back. So all I'm going to do is rewrite my problem to become 4 square root of 10 minus 9 square root of 10, and then push the plus square root of 13 to the back. Now these two right here, since they both have the same irrational component, they are similar to like terms. I can actually do calculations on them. But I'm only going to do calculations on the coefficients out in front. So I got 4 minus 9, and that's going to give me a negative 5 square root of 10. So I don't bring down the square root of 10 and the square root of 10. Those don't cancel out, just like if those were x's. So if it was 4x minus 9x, I would have a negative 5x. Well, 4 square root of 10 minus 9 square root of 10 leaves me with negative 5 square root of 10, just like a variable. And then bring down the plus square root of 13. And this ends up being my simplified problem. Example B, right now it does not appear that either of these are like terms. However, the square root of 48 can be rewritten as the square root of 16 times the square root of 3. And the square root of 16 can be written as 4 square root of 3. So this right here can be written as that. So I can just rewrite the problem as 5 square root of 3 plus 4 square root of 3. And now we can see that these two are similar. So now I can go and do the 5 plus 4, which will give me 9. And the square root of 3, again, is like a variable, just comes along and attaches as one irrational number. Example 6, multiplying radical expressions. Okay, so out here we have a distribution. So we're going to take the square root of 5, multiply it here, and the square root of 5, and multiply it there. Now keep in mind that we cannot multiply rational with irrational components. So the first multiplication, square root of 5 times 4, is just going to give me 4 square root of 5, and all I can do is express it like that. It's just same thing as if I had an n times a 4 here and I multiplied it. All I can come out with is 4n. Since I don't know what the value of this square root of 5 is, I cannot actually multiply it with 4. Then distribute the square root of 5 times the negative square root of 20. So I'm going to bring over my negative. It's going to be a negative. And since the square root of 5 and the square root of 20 are both under the radicals, I can call it square root of 5 times 20, which can be rewritten as the square root of 100. And the square root of 100 is 10. So this then can be simplified even further to 4 square root of 5 minus 10. Now I cannot combine these together because there is no radical 5 over here next to the 10. So I am just stuck with 4 square root of 5 minus 10 as my simplified answer. If you look at B, we have what amounts to a binomial times a binomial. And if you remember back to when we were working with quadratics, we're going to distribute. So we're going to take this square root of 7 times the square root of 7, and that's going to give us the square root of 49. Then we're going to take this square root of 7 and times it by the negative 3 square root of 2. And that's going to give us a negative 3 square root of 14. Remember, we can only multiply the irrational components together. The 3 out in front cannot be affected. Then we're going to come back here and multiply the square root of 2 times the square root of 7, and that's going to give us a positive square root of 14. And then we're going to take the square root of 2 and multiply it here also by the negative 3 square root of 2, and that's going to give us a negative 3 square root of 4. Now we're going to simplify. Up here, this is a perfect square, so that becomes 7. These two are considered to be like terms. So this is a negative 3 plus a 1 square root of 14. So the coefficient of that square root of 14 is like a 1. So negative 3 plus 1 is going to give you a negative 2 square root of 14. And 3 square root of 4, the square root of 4 can be reduced to just 2. So this is really negative 3 times 2, which is negative 6. And as we continue to simplify, we see we have like terms here. So 7 minus 6 leaves you with 1 minus 2 square root of 14. And this ends up being our final solution.